Okay, so I wanted to finish the story about the life cycle of stars and how we generate the heavy elements. So we saw that eventually a star with the mass similar to the sun goes through a phase. It leaves the main sequence and goes through a phase of becoming a red giant. The um, pressure inside the central region of the star becomes very high, as we saw, because all the um, at least in the central region, the hydrogen has been converted into helium, helium being a denser gas. That increases the pressure, which causes the temperature to go up. And when the central region of the star reaches a sufficient pressure, matter becomes or enters a degenerate state. The degenerate state is something, is a quantum mechanical state. The details of this are not important for us. The key fact is that the pressure does not go up with the pressure, with the temperature. So in contrast to a normal thermal state, where if you heat an ideal gas, the pressure goes up, right? But here, in this special quantum degenerate state, you increase the temperature, but the pressure does not go up with it. And as a result, when the temperature reaches 100 million Kelvin, helium is converted into carbon via nuclear fusion. You have enough energy to start this nuclear fusion reaction. It's called the triple alpha process. I have it on the diagram on the next slide. But let me continue the story here. The heating of this nuclear reaction releases a lot of heat, and that causes the temperature to increase. But increasing the temperature increases the rate of this nuclear fusion reaction, which increases the temperature, which increases the rate of fusion reaction, which increases the temperature. So you can see there's a runaway unstable reaction here. As a result, within a few seconds, most of the central region of the star, it will be converted into carbon. Remember, it's mostly helium-4. That helium-4 goes through this triple alpha nuclear fusion reaction in a few seconds. And this event is called the helium flash. And there won't be any more nuclear reactions for this red giant star. Its life as a nuclear fusion reactor is over. So for this is really for the just for the people who are interested on the details of this nuclear fusion of helium-4 to give carbon-12. It happens in a two-step process. You bring together two helium-4 nuclei. These are called, for the physicists, these are called alpha particles. It's the helium-4 nuclei. Two protons. Remember, my protons are the black dot, big black dots, and the open disks are the neutrons. And so they come together in a nuclear reaction, a little bang, I like to call it, and a gamma ray might be given off. This is really going into the details here, but it takes energy to make this reaction take place. Remember, we're at 100 million Kelvin here. It was super high temperatures, 10 times hotter than the interior of our sun at the moment. These are really high temperatures, and you need the kinetic energy of these two alpha particles in order to initiate this reaction, which will actually absorb a little bit of the energy. It's possible that there's even more energy if these things are hot enough. There's more energy available, and some will be given off as a gamma ray. Then you have a very unstable beryllium-8 particle or nucleus. It would normally only last for fractions of a second. But if this is going on often enough, this reaction, you will have, there's a certain window of opportunity where these unstable particles are around, and if they react with another alpha particle, another helium nucleus, then you have the possibility of another nuclear reaction. This one is an energy producing reaction, so you definitely get a gamma ray going off, and you join these two nuclei together and form the nucleus of the stable carbon 12 molecule. Atom, the nucleus of the atom. So this is called the triple alpha reaction. It gives you almost 7.3 mega electron volts for every of energy. A mega electron volt is 1,000,000 electron volt. It's a unit of energy used in particle physics. And you get that for each carbon 12 molecule, nuclei produced. Okay. This is a little quote from the end of a famous poem called The Wasteland. The life of stars with mass similar to the sun, they go out with a whimper. That I guess the implication is not with a bang but a whimper. Is the quote from The Wasteland by T.S. Eliot. But the point is they go out quietly as opposed to dramatically with a bang. So even if this the flash of helium, this rapid conversion of helium to carbon, is a very dramatic event in the interior of the red giant star. At the surface, not much happens. I guess I'd like to emphasize just how dramatic this flash of helium event, helium flash event is. So remember, it took if we're talking about the sun here, this will happen for the sun in several billion years. It will have taken 10 billion years to produce all that helium in the core or central region of the sun. And then within a few seconds, this triple alpha process is going to convert all that helium into carbon. It's an extremely dramatic event, but nonetheless, it's a very internal process, and because the energy is mostly absorbed by other processes inside the star, so the net result is a quiet thing at the surface. But now there are no more nuclear reactions for this star, and so it has it's no longer generating heat. Its temperature will increase. That's because the star will start to fall in on itself. Remember, it's a red giant at this stage. It's a much bigger volume than its current state. As a result, its luminosity will lower. The rate at which it emits energy drops. As a result, the location of the red giant star on the Hertzsprung-Russell diagram will migrate down and to the left, and I'll do that to my right, which I think is your left, because its temperature is going up, which was to the left on the Hertzsprung-Russell diagram, but its luminosity is going down, so it goes down along the vertical axis. It then terminates its life in what we call a white dwarf. Its radius will correspond to the size of the Earth, but its mass will remain still approximately 1 solar mass. So in other words, it doesn't lose much mass in this whole process. These nuclear reactions are very efficient at converting a little bit of mass into a whole lot of energy, and as a result, the mass of the sun does not, it's still of the order of 1 solar mass, but its volume, when it finally cools off and shrinks to a white dwarf, its volume will be about that of the Earth, and therefore its density will be about 1 million times that of water. And just a little caveat, this helium flash, I said it happens for stars with mass similar to that of the sun. To be a little bit more precise, it's in this mass range here, where for stars with this is the initial mass, the mass when it first entered the main sequence, the Zams line. Should be in this mass range here. And if you're not used to reading that, I'll convert it to words for you. It's between 80% of the solar mass and 2 times the solar mass. So the mass, if the initial mass of the star is less than 80% of the sun's mass, then you do not have enough pressure in the central core to obtain this 100 million Kelvin to kick off these the triple alpha process of converting helium to carbon. And if you're so this green flash, or sorry, helium flash does not take place. But if your mass is above 2 times the solar mass, then things are more complicated and other processes intervene. We can only discuss some of the astrophysics here. We can't cover it all, unfortunately. So the sun, just a sort of summary on what happens to the sun over its life cycle. We're currently on the main sequence where it's been around for 4.5 billion, a little over 4.5 billion years, and it's been converting hydrogen into helium through this the proton-proton chain, some of the details of which we looked at in detail, and this will convert during this full about 10. It'll do this for about 10 billion years, and so it's like that's its life on the main sequence, and it will convert about 10% of its hydrogen into helium. Why only 10%? Because this conversion process takes place in the central region of the sun, where it's hot enough to attain this fusion of 2 protons to give deuterium. It will continue its life on the main sequence for another 5 billion years, and remember, its luminosity gradually goes up as we explained earlier, as the density increases with the increase in the helium levels. It becomes a red giant, augmenting its diameter 100 times. Its luminosity will go up 1,000 times. It will persist as a red giant for about 3 billion years. And unfortunately for life on Earth and the inner planets will be evaporated, and but interestingly, at 30 astronomical units, Neptune will receive the same solar radiation, approximately the same intensity of solar radiation as the Earth currently gets. And so I propose as an exercise for you to think about where our descendants can go to sort of survive this red giant phase of the sun. And I've suggested one possible consideration here would be that we go live. Of course, we can't live on Neptune, but we could, a satellite of Neptune would be a good idea. Unfortunately, there is a moon of Jupiter, of Neptune, called Triton, which is not currently habitable because of its atmosphere of carbon monoxide, but Unfortunately, it has other problems. This is meant to be a sort of a fun thing to think about. It's an extremely important problem because the fate of our descendants depends on it. But fortunately, we have billions of years to solve this rather important problem. Okay, we still haven't addressed the question about where the heavier elements come from. So I just want to very quickly, briefly tell you where the heavier elements come from. So stars with greater initial mass, with initial mass more than 8 times the solar mass, can produce elements between helium and up to iron by nuclear fusion reactions in their cores. And we've sort of looked in detail at how you can get, for instance, carbon, but you can produce these heavier elements in nuclear reactions in the cores of heavier stars. But we don't have time to look into this in any more detail. But stars of these larger mass end their life in a dramatic way. They go out with a big explosion that's called a supernova, and this supernova will make the elements heavier than iron. It's hard to produce elements heavier than iron because iron has the most stable nucleus. If you for heavier for greater atomic number, so heavier nuclei, it actually takes energy to create those nuclei. So as opposed to the lighter nuclei, you release energy. Remember when we took the helium and brought them together, it was very difficult to do so. It took more than 100 million Kelvin temperature to do so. But if you could, then you could liberate mega electron volts of energy for each carbon you produce. That sort of production of energy stops at iron, and so the elements heavier than iron are produced in other ways, and an important way is the supernovae, which are these explosions that end the life of a star. So a little more about this explosion. It's a dramatic event. It only lasts a couple weeks, but during this period, the exploding star will be brighter than the rest of its host galaxy. I'm assuming a typical galaxy like our Milky Way galaxy. So these supernovae are important sources for the elements heavier than iron, but they're not the only source. You can produce heavy elements by other processes, for instance, the collision of neutron stars. We don't understand all the processes that give the heavy elements. I'll point you to some seminars that discuss this. It's called the R process. I'll just leave you with the thought that we are literally made of stardust. So here's some of the videos of their online scientific seminars of people discussing the how you can produce the heavier elements. And if you're curious on the things I work on, I don't actually work on astrophysics, but I do work on most recently I've written a paper about Einstein's theory and explaining the geometry of black holes and how that relates to the geometry of the universe, actually the expanding universe. So it's a little bit different than astrophysics, but it's more conceptual and related to cosmology. But if you're interested, I'll be happy to discuss that with you.